Hello students, welcome back to the series Coordination Chemistry. In this module, we are discussing about the reactivity of complexes. Here we discuss different reaction that complexes undergo. That is, metal complexes undergo variety of reactions such as electron transfer reactions, ligand exchange reactions, substitution reactions, addition reactions, etc. So, these complexes, this transition metal complexes, they undergo a variety of reactions that will be studied in this module. And before that, we have to understand what are labile complexes. Some complexes are labile and some are inert. Then what are labile and what are inert complexes? The complexes that react rapidly are called as labile complexes. So, labile complexes, they undergo reactions very rapidly. And in labile complexes, metal ligand bonds are easily broken. We know that if the complexes react very rapidly, then in that complexes metal ligand bonds will be broken very easily. Then only they will be able to react very rapidly. And that is, they shows high reactivity. And also in the labile complexes, the reactions are within, that is, their T half is less than 1 minute. So, if the reactions having their T half less than 1 minute at 25 degrees Celsius are kinetically labile. So, these are the characteristics of the labile complexes. And now, what are inert complexes? The complexes that react very slowly are generally called as inert complexes. And in inert complexes, we have the metal ligand bonds, they will be very difficult to break. That is, metal ligand bonds are broken very slowly, or it is very difficult to break the metal ligand bond. And also the rate of ligand displacement is obviously in inert complexes, this rate of ligand displacement will be very slow. And the reason is that there is a large activation energy needed for the bond breaking and making in inert complexes. And in these complexes, we have their T half greater than 1 minute. And if the T half is greater than 1 minute, that complexes are generally kinetically inert complexes. So, these are the characteristics of inert complexes. We have the complexes which react very slowly are called as inert complexes, and in inert complexes metal ligand bonds are very slowly broken, or they need very high activation energy for the reaction, and their T half is always greater than 1 minute. Okay. And now we are moving to the ligand substitution reactions. I have already told that the complexes, metal complexes undergo different variety of reactions such as substitution, addition, etc. And now we are discussing about the ligand substitution reactions. In the ligand substitution, we have it involves the exchange of one or more ligands. See, in the reaction, in the substitution reaction, there an exchange of one or more ligand occurs. We have an initial complex. In that complex, we will have some ligands, and that ligands will be substituted by some other ligands in this ligand substitution reactions. And this substitution reactions can be represented as like this: MLX X plus Y giving MLX Y plus X. And you know that if you see the reaction, the initial complex is MLXX, means M is the central metal atom, L is a ligand, and X is the number of ligands, small x. And this capital X is the leaving ligand, that is the ligand which is supposed to leave the complex. And that will be reacting with the entering ligand Y to form MLXY plus the leaving ligand X. Okay. So, X is the leaving ligand and Y is the entering ligand or entering group. And in ligand substitution reaction, they may proceed through SN1 or SN2 mechanism. So, two types of mechanism are proposed, that is SN1 or SN2. So, ligand substitution reaction may proceed either SN1 or by SN2 mechanism. So, this is the general representation of the reaction. So, we have to discuss first dissociation mechanism or dissociative reaction mechanism or SN1 mechanism. Dissociative reaction mechanism means first a dissociation happens and then only the ligand will be entering. The entering ligand will be attaching to the complex. So, the general reaction can be represented as like this. MLX-X means we have the initial complex MLX-X. That complex will be initially removing the leaving ligand X, that is MLX-X giving MLX plus X, that is initially this X ligand is being removed, that is being dissociated. And in the next step we have this MLX will be combining with the entering ligand Y to form MLX-Y. So, this is the general mechanism or general reaction of a dissociative mechanism. First dissociation occurs and then only association of the incoming ligand happens. And what are the characteristics? MLX is the reaction intermediate. See the reaction is MLX-X giving MLX. So, this MLX is the reaction intermediate, means the species which are involved in between the reactants and product, that is intermediate is MLX. So, we have the reaction intermediate MLX, and also our next characteristic is it is a two-step process. How it becomes a two-step? First a dissociation occurs and then only the entering ligand is coming and attacking. So, it is a two-step process. That is, first step is the slow step. First dissociation step is the slow step and the second one is the fast step. And we know that the rate determining step is the slowest step, right? And that is why the dissociative step is the rate determining step, that is why it follows the SN1 mechanism. So, only one species is involved in the rate determining step, that is the complex MLX-X only is involved in the rate determining step, that is why the reaction is SN1 mechanism. And we have the formation of the intermediate in this mechanism, which is the intermediate formed, it is MLX. MLX is the ML suffix X, that is MLX is the reaction intermediate. And also the coordination number of the reaction intermediate is lower than the starting material, and I have already discussed what is coordination number for a transition metal complex. Coordination number, see this is the initial complex MLX-X and this MLX is the reaction intermediate. So, the starting material is having this coordination number, that is if LX, if it X, small x is 3, it is L3 and X means 3 plus 1 4. So, the coordination number of this complex will be 4, right? And if X is removed, 1 is removed. So, what will be the coordination number? It will be coordination number of the intermediate, it is only 3. So, if the starting material is having the coordination number 4, the intermediate will be having coordination number 3. So, 1 less, right? This is what the coordination number of the intermediate is lower than the starting material. Always in dissociative mechanism, the coordination number of the intermediate formed will be lower than the starting material. And we know that this here, why it is called as SN1 mechanism, only one species is involved in the rate determining step. Which is the species? The initial starting material, that is MLX-X. That is why it is called as SN1. It follows the SN1 mechanism. And now moving to the next type of mechanism, that is associative mechanism or SN2 mechanism. As the name suggests, here the initially association happens, that is the incoming ligand will be associating with the starting complex and then only the dissociative step happens. So, the mechanism can be generally represented like this. We have the starting complex MLX-X, X is the leaving ligand, Y is the entering ligand. And since it is associative mechanism, initially what happens, this Y will be attacking or associated with the starting complex, that is it forms MLX-XY. So, association happens initially. And now in the next step, dissociation of the leaving ligand. Which is the leaving ligand? X is the leaving ligand. Now in the second step, this X leaves the product, right. So our product is MLXY. So this is a general mechanism of associative mechanism. What is the peculiarity of associative mechanism? Initially association happens and then only followed by the next step only we have the dissociation step. Okay. What are the characteristics? It is a two-step pathway. Why? Because we have two steps involved. So it is a two-step pathway. And two species are involved in the rate determining step. Why? Because see, this first reaction is the slowest step. In first reaction, how many species are involved? The MLXX, that is a starting complex, as well as our entering ligand Y is involved in the rate determining step. That is why we say that two species are involved in the rate determining step. Or we can call it as a second order reaction. The reaction is a second order reaction. Why? Two species are involved in the rate determining step. And this type of mechanism is usually common for 16 electron species, because coordinatively unsaturated species will be undergoing this associative mechanism. Because why? Because since they are coordinatively unsaturated, they are able to accept a group or electrons to the complex. That is why 16 electron species are always undergoing the, so generally 16 electron species will be undergoing the associative mechanism. And now if we are looking at the coordination number of the intermediate, and before that I must say which is the intermediate in the complex. See, the reactive starting complex is reacting with the entering ligand to form the intermediate. Which is the intermediate form? It is MLXXY. So intermediate is MLXXY. What about the coordination number of the starting material and the intermediate? We have the starting material this, and one coordination number has been increased for the reaction intermediate, right? In this complex we have only X, but in the reaction intermediate Y is being coordinated with the complex. So the coordination number is increased for the reaction intermediate when compared to the starting material. That is what we are discussing. So the coordination number of intermediate is always higher than the starting material. And now this is all about the substitution reactions generally, and we have to discuss about the substitution reactions in square planar complexes. We have studied the different types of complexes are there: octahedral, tetrahedral, square planar, etc. Particularly we have to discuss the substitution reaction in square planar complexes, which is very important. The substitution reactions in square planar complexes, they mainly occurs through SN2 mechanism. So they mainly follows the SN2 mechanism. SN2 means two species are involved, means the starting complex and the entering ligand will be involved in the rate determining step. And generally you can represent the reaction like this. In the square planar complex we can actually substitute the value of small x, y as 3. Why? Because the square planar complex number of ligands will be 4. So I can generally represent like this: ML3x. So 3L ligands are there plus 1, so 4 ligand, and we have totally 4 ligands present in the complex. And now X is the leaving ligand, Y is the entering ligand. The reaction can be generally represented like this: ML3X plus Y, giving what will happen? ML3, Y will be entering the complex and X will be leaving, where X is the leaving group and Y is the entering group. And the rate determining step will be rate equal to K1 into concentration of these two species are involved in the rate determining step. So the concentration of ML3X into concentration of Y. That is why it is an associative or SN2. It follows the SN2 mechanism. Okay. So this is how the substitution in square planar complexes happens. And now in square planar complexes, how we know the square planar complexes follows SN2 mechanism? There are evidences, because the steric crowding slows down the reaction rate. If we have bulky ligands within the complex, then the substitution is very slow. So, we understand that since bulky ligands are there, if an entering ligand is coming there, obviously the reaction is very difficult to happen. That is why we can understand, this is how we understand that SN2 reaction is the mechanism in the square planar complexes. So, the evidence is steric crowding decreases or slows down the substitution in square planar complexes. And also the reaction is stereospecific, and I will be explaining how it is stereospecific by explaining the mechanism. This mechanism is as follows. See the mechanism, you can see the square planar complex generally represented as M, A2, T and X. And simple, I have given a simple notation for all the ligands. And X is, we have X as the leaving ligand and Y as the entering ligand. See the Y is coming, it can either come above or it can enter below the complex. In this example, it is entering above the complex. This Y is coming above the complex and Y is attaching there. And now we know that initial starting material is a square planar complex. After this Y being attached in the complex now become a square pyramidal intermediate. Now we have the square pyramidal intermediate, and after the intermediate formation, this square pyramidal intermediate will be undergoing some kind of intramolecular rearrangement to form a trigonal bipyramidal intermediate, and then the leaving ligand Y will be leaving the complex. This is how the mechanism happens. And see, Y is coming above the plane and attaching the complex to form a square pyramidal intermediate and undergoing an intramolecular rearrangement in such a way that this X, the leaving ligand X now takes an axial position for a better release of the ligand, and now the X will be in the axial position in the trigonal bipyramidal intermediate, followed by the removal of X, and finally we get the product. The in place of X, Y is there in the product. That is why the reaction is stereospecific reaction. Okay. And now here is a mechanism which is written as a summary. First, the entering ligand can approach from above or below the plane to form the square pyramidal intermediate, and this will undergo an intramolecular rearrangement through a trigonal bipyramidal structure to form a new square pyramidal intermediate, or it is actually firstly it follows a trigonal bipyramidal intermediate followed by the square pyramidal, and now the this leaving ligand X will be in the axial position, and this loses the leaving group X from the axial site and to form the product, and thus we can say that the stereochemistry is retained in the complex, or we can say that, or we can conclude that the reaction is stereospecific. Okay, so mechanism is as explained. And now we have to discuss different factors that affect the rate of this reaction. Different factors are affecting the substitution reaction, and first one is the effect of labile group. And we have discussed what are labile complexes or what are inert complexes. Now obviously labile group means the group which are easier to leave complex. So this is the order of lability as seen in the in the sequence. The Cl minus is having greater lability followed by bromine, iodine, etc. In this series you can see Cn minus etc. have a less labile nature. So if Cl minus is there in the complex, that ligand will be easily removed from the complex. Okay. So the effect of labile group is as follows. You have to study the order of lability of the ligands. And now the second factor is the nature of the entering ligand. See, in all the examples, Y was entering. Generally I have written Y as the entering ligand. So this nature of this entering ligand is also very important in this substitution reactions. If the entering ligand is able to attack the complex more effectively, that complexes there, that substitution will be very easy. And also we have another factor, that is the size of ligands, size of the other ligands inside the complex, because in the if we are discussing about the square planar complexes, all the other three ligands, if they are sterically crowded ligands, it will be very difficult for the entering ligand to come and attack. So the size of the other ligands will be affecting the rate of the reaction. And now we have another factor, that is effect of solvent. See, we have generally speaking about the solvents, we have water as the solvent. Usually some of the reactions will be having H2O or water as the solvent, and this H2O itself can act as a ligand also. We have seen that H2O is a ligand. In such cases, if the reaction is being done in a water solvent, what happens? This water can act as an ligand before this this incoming ligand being attacked on the complex. So we have to take into consideration that also. And if the solvent is having less attacking nature than the incoming ligand, then what is the factor that affecting the rate of the reaction? It will be the concentration of the ligand. So the concentration of ligand, if the concentration of ligand increases, the reaction will be increasing, provided the solvent should not be able to attack the complex. That is to be noted. So the effect of solvent is an important factor. And now another factor is effect of charge on the complex. See, we know the what is the charge, how is the complex is having the charge, everything has been discussed in the earlier classes. So as a positive charge on the complex increases, the rate of substitution also increases. That is the point. If the charge on the complex is more, then the reaction will be more faster. That is it. And now finally another factor, and the final factor, that is the trans effect. Then what is trans effect? It is a labilization of ligands which are trans to certain other ligands having trans directing nature. See, some of the ligands have their capacity to direct the incoming ligand to attach to their trans position. Such ligands are called as trans directing ligands, and that will be discussed in the next module in detail. In here you have to just understand that trans effect is an important factor that affect the rate of a reaction. That is, if the trans directing ability is more, then the reaction will be, then the incoming ligand will be directed trans to the this ligand which has the trans directing property. That is it. So trans effect is an important factor that affect the rate of the reaction. So these are the factors that affect substitution reactions. There are 6 factors that affect. All the factors are equally important. So in this module we have discussed the different reactions that this coordination complexes undergo, like substitution reactions, and what are the mechanisms that these complexes follows in the substitution reactions. We have studied different associative and dissociative mechanism, how the associative and dissociative mechanism occurs, etc. What are the intermediate formed, what are the characteristic of these mechanisms, etc. And we have discussed, we have studied in detail the substitution reaction in square planar complexes also, and the mechanism that follows the substitution in square planar complexes. And finally we have studied what are the factors that affect the substitution reactions. We have 6 factors affecting, and among the factors we have seen that the trans effect is an important factor that affect the rate of the reaction, and in the next module we will be discussing in detail how the trans effect is affecting reaction, what are the theories of trans effect, etc. That will be discussed in detail in the coming module. And thank you all for watching now. Thank you.